Hi, everybody. Sorry for the lack of tunes. Okay, what do you got for me today? Listening recommendations. I don't know. If you have never heard it, it's an old one with the Richard D. James album by Aphex Twin. It's good. All right, what do we got? Just because I was listening to it while working. It's like a couple decades old now. So what do we got on our agenda in theory? I should say first, my TAs, one of them pointed out we have really important survey data coming. So I'm actually going to wait till next Monday so that I have that, and that'll be more interesting. So then we'll have taken into account how our most recent weeks have had less stuff due. So I want to, and like how we've adjusted the homework one workload. So I want to see how that goes first. So I'm going to wait till Monday on that. So in theory, today we're talking about, oops, wrong. Lecture day. So yeah, we got our abstract data type sets, maps, binary search trees, and also of course getlit and whatever else you want to talk about. So yeah, what do you guys have in mind? I've started working on getlit. I've got add, init, and commit partially done. I did this project a long time ago, spring 15, the first semester we ran it. I haven't done it since. I'm trying and get it back in my brain. Tweaking this back as I go. Okay, I'm ready. Nothing? Everything makes sense? We're all good to go? I'm gonna be a very good webcast if you guys are asking questions.
Okay, I've got one. Could you throw us a trickier asymptotics question?
Like an exam level?
Yeah. Do you mind if I just grab one from an old exam? Because that way.
I don't know.
No.
All right. Let's see. I'll just grab one from last semester so I can get them quickly. Yeah. Let's see what we got. So I am spoiling this for practice later, but let's see. Let's just do all of these. See how it goes. I can't copy and paste. Okay. I'm not sharing my screen, so let me do that. All right. So this is just the fall one. There's so many old asymptotics problems, so I don't feel bad spoiling this. Here's our first one we're going to do. We got some code, and looks like a lot of loops. Let's see. It's kind of a sneaky one. Okay. Do you want to talk through it, Ethan? Let's talk about
it. I'm game to talk about it.
Great. All right.
Okay. So I'm pretty out of practice with this
Sure.
stuff.
Yeah. This one's really mean, so it's like a strange question for me to ask you, but here we go.
Okay, so for the most exterior loop, that's just gonna be like, that would just be like constant, right? Because that's just 3 times no matter what.
Yep.
So then for the second one, wait, isn't that also gonna be
sure is. That's why I said it's a mean one. Yep.
Okay, so then the third one, that's gonna be logarithmic because it's less than n. Oh, thank you. It's less than n, but it's increasing like 2 times. So that makes it logarithmic. And then the fourth one, wait, the fourth one's also constant.
That's right.
Wait, so this is just log n?
Yeah. Just log in. That's it. You got it. Okay. Sounds a little mean, but that's what it was. All right. Good.
Oh, nice.
Okay. Here's one. This one's a little richer. So this one requires us to know what a hash set is. So next. All right. I'll have to save that one for later once you know what hash sets are. Okay. Oh, this one's interesting. Okay. So this one, it's asking you the runtime to call nested sum of x. So I guess the first question I would ask myself is, oh yeah, I like this one. It's rich. Okay, so nested sum here. What do you think the runtime of nested sum is as a function of n? Where n is the length of the array.
So the most exterior loop, so in this function, the most exterior loop is going to be linear because it's for I and X.
Right.
And the second one for J and X, that's also good. So that's going to be n squared, right?
Right. So a nested sum takes n squared time to run.
Yeah.
Okay.
So then nested sum of nested sum. Oh, Jesus. Is it going to be n to the fourth?
Well, it's an interesting question. It depends on what nested sum returns, right?
Oh, it returns the new. Oh, wait a second. Wait, no, it returns a new list.
And how big is that list?
So it's I plus J every time it. Wait. So the list will be like twice the size, won't it?
It'll be the squared of the size.
Oh, squared of the size. Oh, so it's more than n to the fourth.
Well, it's actually, well, you got to think about it.
Well, I do have to think about it.
Maybe I need a notepad window. One sec. Let me go nab code.
Oh my God, this is getting tricky.
All right. This is fall 20 asymptotics. Oh, can you still see the code, by the way?
Yeah, we can still see it.
All right, cool. I'm not sure if I took it away. There was a version of Zoom for a while where if I put another window on top, it would lose track. Okay. I'm setting something up in a notepad window so we can explore this problem and variants of this problem. Okay. I'm about to do the same thing, just in a Java window. Run a Sublime text. Here we go. All right. Okay, so here's that same thing you were just looking at. Right. So I'm going to break this on 2 lines just to make it even more clear. There we go. All right. So basically, it creates a new list. I'll call this thing x2, I guess. So it creates this new thing, as you noted, right? So there were some observations you made that were both correct. Observation. Nested sum took x.length squared time. Observation. x2 is of length, x.length squared. Okay, right? Maybe let's call them as. Happy with those 2 observations? All right, cool. So then, how about this one? How long will this call take to run?
So, oh, were you gonna say something?
No, go ahead.
Wait, so if it's gonna run the square of this length, so it's gonna do an n squared algorithm on a list that's a square of the original size.
Right.
So this thing itself should take n to the fourth, right? So then if it's doing n to the fourth and also n squared.
Why do you say n to the fourth and n squared though? Because this thing is n squared?
Well, no, because the first thing didn't.
Oh, right. That's n squared, and this one's n to the fourth. Yeah, okay. So the runtime is n squared plus n to the fourth.
Oh,
basically.
and that's just order of n to the fourth.
Yeah, right.
Oh, I see.
I see.
Okay.
Yeah. So let's do some variants of this.
Yeah, so wow.
It's a weird problem. So let's do some variants where we. Okay, I'm gonna make a new problem. Okay, nested sum 2. All right. I'm just changing it up a little, and this time I'm going to do no, that's not what I want though. Oh, okay. Yeah, actually, what I'm gonna do. Here we go. All right, it'll be worth it. 1 sec. Let me just create this problem. Okay. All right. Now that we have this new version, nested sum 2. It's a different problem. Let's try and solve this one. And actually, I'm gonna make it on 1 line. Okay, so what do you think the runtime of this will be? I see silent discussion.
Oh, my bad. Sorry.
Yeah, wait. So what we were talking about is, so before in the last thing, didn't it add to total every single time in the J for loop, in the inner for loop?
Right, yeah.
Oh, I
But this
see.
time it's only adding at the end of it. So the new list isn't going to be a square of the old size. It's just going to be double.
You're right. Okay.
Right. So the runtime for this, runtime is n squared. Return list is of size n.
Yeah.
And so what's the overall going to be?
So it's a return list of size on the order of n, right? Because
yeah, right. Yeah.
So then that's also going to, so then.
Why, out of curiosity, why do we say the size is going to be like in order notation instead of just like what the size is?
It's n, sure.
It's as it, oh, okay.
Yeah, I mean, just because that's what other guy said. That's all I know you asked. Sorry, other guy.
That's Rohan. Sorry.
Oh yeah.
Rohan.
So then the second one, so you're running an n squared twice. So is that just going to be order of n squared?
Right. So this one is the overall runtime is big O of n squared plus big O of n squared, which is big O of n squared. So it's kind of cool because it's like, you know, somewhat similar pattern, right? That you do nested sum. I'm gonna take this away. I have to scroll it off the screen. And I'll do the same notation here. Right. So the difference is like these two pieces of code, it's a nested function with n squared runtime in both cases, but this one has n to the fourth runtime. This one has n squared runtime.
It just depends on where you're modifying the list.
Or like what you're returning, right? Yeah.
Okay.
Yep.
That's
fun, right? So it's rich. All right. Let's see. Okay. Should we do more? Anybody else have other questions? I'm happy to keep doing old asymptotics problems. I mean, this is the highest skill ceiling thing in the whole class. So
I think Dana might have.
Wait, I have another one.
yeah, please.
So on the Asymptotics 2 study guide,
Yeah.
problem 6, but it's actually problem 4 from spring 2017 midterm 2.
Spring 2017. Okay, midterm 2,
Yeah.
problem 4. Okay. Mm-hmm.
And it's part B, but then the second function.
Here, F5. Okay.
Yeah.
Oh yeah, I love this problem. This one's so good. I was proud of this one. Okay, let's bring it into a window we can manipulate. Okay. Let's see, do I need a, trying to think, do I want code or do I want notepad? I think I want a paint window. Let me copy and paste this thing. Okay. Sorry, my office hours APM is not high enough. Okay. All right. Here we go. So we're gonna try to analyze. This is a weird function. So what I'm gonna do is I am going to plug in some values and see what happens first, because I need to understand what it's doing. Let's say I do I don't know, 120, 135, 262. Why did I pick these numbers? Just because I noticed the arguments are getting divided by 10. So I want to pick something big. All right. If n is less than 10, return. Nope, not going to do that. Otherwise, we do for n, I equals 0, I is less than or equal to n mod 10. Okay, so it's going to do this 5 times. It's this digit, n mod 5, or n mod 10 is this right here. So that's going to make 5 calls to F5, 13, 26. Same thing over and over. 13, 26, and so forth. Okay, so key piece of advice for people watching this or here right now. Plug in some numbers, get a sense of what's going on, because I don't have the abstraction skills to just immediately go, oh, okay, I know what's going on. All right, next up, then each one of these is going to make 3 calls to 1 and 2. 1, 2, F5, 1, 2. All right, and so forth. All right, so we have 5 calls here. And then each of those has 3 calls. All right, question. We need to pick a cost model. What do you think, Dana?
Calls to F5.
Sounds great. Why is that safe? Well, let's see. So the amount of work in each one will be constant, because this right here, this loop, though it is a loop, this number is always going to be less than 10. So it seems perfectly reasonable to count F5 calls. Like, the reason I would run into trouble is, let's imagine we had a for int I equals 0, I is less than n loop or something. Then we want to count something like in that inner loop potentially. I don't know, maybe. Anyway, I like F5 as a cost model. Cool. Okay, so how many total calls do we have for 135, 262? We had 1 plus 5 plus 5 times 3. Right. So that's the total number we had here. Yeah. Okay. So there were 21, assuming I didn't mess anything up. Let me know if I did. Yeah. Okay, let's try again. F5 of, well, 2,165. And then, I don't know, 8, right? Like, I observed that the M doesn't really matter. It doesn't do anything. It's just some number. Like m doesn't get used anywhere other than getting printed. So if I do that, oh, yeah. So if I do that, this time I will have 1, then 5 calls because it's based off this digit. And then I'll have 5 times 6 at the next level. Sorry, what's my pattern here? 1 call, 5 calls, 5 times 3 calls, and then we were done. So now it's going to be 1. I'm just kind of observing the pattern. 1 plus 5 plus 5 times 6. I guess plus 5 times 6 again. So I think the total number of calls, and we have to think, maybe be a little careful about this, but it should be 66 calls. Does that sound reasonable? Anybody detect any issues with my reasoning? Oh, someone says there might be an off by 1 since it uses less than or equal to. Right. Okay, I was off by 1. Thank you. The observation was there were actually a call for 0, 1, 2, 3, 4, and 5. Okay, so sorry, we're off by 1. Thank you. Because there's 6 calls. Yeah, there should be 4. Let me just rewrite this instead of trying to draw over it. We have the technology to erase. All right. There we go. Look at that beautiful. This looks bad. Sorry. 1 plus 6 plus 6 times 4. Okay, 24, 30, 31. Okay. And keep our 1. Great. Can even reuse that dot. Okay, cool. 31. Okay, so next up, let's just redo this again. What it actually should be is 1 plus 6 times 7 plus 6 times 7 times 2. Okay, that's going to be the number of calls. All right, happy with this? Okay, so 70, 35, 6, and 1. Some number like that. Okay, again, the exact number doesn't matter. It's not what we were asked, but it could happen, right? You can imagine an exam question that says get the exact count. So 105 plus, sorry, yes, 105 plus 6 plus 1. 105 plus 6 is 111, 112. Cool. Okay, so what's the overall pattern then? It's like how would you describe the total number of calls here? So we need to come with a big O notation answer in terms of n, I think. Actually, what does the problem say? Give a big O. Yeah, okay, cool. All right. The question is to give the answer. Okay, so let's think about some different possibilities. Is it fair to say that this thing is big O n? Would that be a true statement? Might not be the best, but it might not be the tightest bound. But is this true? Like, I know this is true. It's true that it's big O of, like, you know, n to the n factorial. Like, there's no question it's smaller than that. I'm just picking that as a straw man. What about n? Can we say that's better than, it's never going to grow faster than n? Well, we observe is that if we made a little table here of n's versus whatever the runtime is, we filled in 2 rows of this table. We have that if it's 135, the number of calls, I guess I should be using R here. I should be using my cost model. So maybe C then. So C of n is my cost model. It's the number of calls to the function. Wow, that doesn't look like legible symbols. So 135 gives us 31. 2,165 gave us 112. So just to be absolutely clear, we're trying to figure out the trend in this chart here. I'm going to clear out this stuff because we're not using it. Okay. So what do you think? Is it safe to say that this thing is growing slower than n?
Yeah.
Right. Yeah. I mean, the argument basically is just that it's the runtime is the number of calls. It's like the I don't know how you describe this function exactly, but yeah, seems like this is safe. Okay, can we get an even tighter bound somehow? Let's say we pick some really big number. I don't know, 99999. Right, exactly as Patrick just noted. I'm picking 9 because it seems like this worst case number. So if we have 9999999, the overall runtime is going to be roughly like what? Like we can figure out C of n here, roughly.
Is it 9 to the 7?
Well, remember it's one more than that, right?
Oh.
It's like it's always it'd be 10 to the 7.
Okay.
Right, 1, 2, 3, 4, 5, 6, 7. Yeah. So this number is on the order of 10 to the 7th, and C of n is 10 to the 7th. So I think actually this is probably the answer. That is just n. Right? It's not going to be anything slower than n, because this is, yeah, if we think about this table, if we do only the 9s, it would be 9 takes 1, 9, 9 is going to be, it's not 10 to the 7th exactly. This is just a rough count. Let's do the exact count for 99. So it would be 11 for 99. For 999, it would be 1 plus 10 plus 100, which is 111. Right, okay. So does it make sense, the pattern we got here? So the lesson here is basically that, you know, these asymptotic problems can be arbitrarily weird. That's the key thing to realize. Just really got to dig into them. So it seems pretty clear that for a given n, the cost model, if it's all 9s, is going to be, assuming I don't have some off by 1 error again, n divided by 9. So it looks like it's just linear. Yeah. Okay. Yeah. Was that the answer in the answer key? I feel pretty strongly about it. But...
Yeah, it was.
Okay, so that's the argument. It's an obtuse argument. But yeah, it's a hard one. Another way to think about it is it's 10 to the log base 10. Right, yes, okay, yep, which is n. Okay, and that's a reasonable thought too. Yeah, 10 to the log base 10 of n is the pattern. This is basically what we're, like this part here, as Consuelo notes, it's basically this rough pattern. And so this thing's just n. Cool, great. All right, that's fun. What's next? Again, the key, asymptotics problems, they're arbitrarily weird.
Right, if no one's going, I asked this questioning a couple of days ago, so I guess it could kind of be a weird asymptotics problem. So for merge sort, basically we take two separate arrays and then, or sorted arrays, and then you compare the first element of each one, right, to see which is bigger.
Yeah.
And so I was thinking it seems kind of inefficient because if you have one array that's I don't know, 1,000 or something, and then the second array is 1, 2, 3, 4, 5, you're gonna compare the 1 to the 1,000 and the 2 to the 1,000. There's like sorting algorithm that's it kind of like takes those runs and
yeah. Basically, what you're observing is that let's say we have 2 arrays that look like 1, 2, 3, 4, 5, and this one looks like 90, 91, 92, 93. You don't need to do a bunch of comparisons. You can just say, this number is smaller than this number, so let's just copy them directly, basically, right?
Yeah.
So that's actually something known as a adaptive, right? Yeah. So merge sort can be made adaptive. For example, if the largest item in the left array is smaller than the item in the right array, just copy everything in order. Left item, no need to do any comparisons. So this word, let's see, I'm trying to find, I'm gonna double check that this is the exact right word. Yes, so if I share my whole screen, so an adaptive sort, which is something we haven't really talked about, is a sorting algorithm that takes advantage of existing order and can be faster. Insertion sort, I guess, is another example where it's very fast on, we'll talk about the sort later in the semester, but it's very fast on arrays that are almost sorted. But yeah, so merge sort does have that property. There's other tweaks you can make to merge sort. So if you make this tweak and many others, you end up with Tim sort. So what's Tim sort? Tim sort is just a variant of merge sort that has all these little tricks in it. It is the sort that Python uses, by the way. Yeah, so let's see if I can find the run size. Okay, where's that trick? Okay, they don't list it explicitly here, but yeah, great observation. And so if you do that, then the best case for merge sort might be different. Though I think it's still in login, just faster in login.
Right, because like you can like interweave them so that the like largest elements are within each other, right?
Well, actually, here, I'm going to give you a trivial example of how the best case for merge sort can be n. So let's imagine that step 1 of merge sort. Check if array is sorted. This is theta n time. So stop. So if you add that optimization to merge sort, then its best case becomes theta n. Make sense?
Yeah.
Yeah.
Right.
Cool. But yeah, that's a great optimization, and real implementations of merge sort absolutely do that.
Cool. Thank you.
I wonder if mergex in the Princeton algorithms textbook does this. I suspect it does. Let's see. Right. So if this item source. Yes, it does it. That's what this line of code does. Now that I look at it. So this is doing what you suggested now. Cool. All right, what's next? If they don't have anything, Dana, you can ask me more asymptotics questions from old exams or wherever else. Reminder, I'm happy to talk about whatevs. Getlit included, lab 6, whatever you got. In lab 6, I'm excited. Okay. Trying to print stuff in lab 6, but they're not printing. Oh, that's interesting. Do you want to share your screen? I'm okay with it if you're okay with it. That's a pretty weird one. Cody, are you comfortable sharing your screen? Oh, you don't have it up right now? Okay. Yeah, that's a very strange one. In Java, at least. Noah, what do you mean when you say the print? Oh, yeah.
Okay, so like I was having the same issue. Where like, in make check,
Yeah.
print line statements, but it would just give me an error even though in the debugger there was like no error. I didn't know what's going on.
Huh.
But yeah, if you, for some reason, if you, or at least my code was wrong because I had like the directory was incorrect or something. So even though my code like works for my own test, it didn't work in the make check because I guess like it only checks in the .capers directory and not if you have a slightly different class.
Huh. Let's see. All right, let's look at, I mean, the make file might be intercepting output and you can't see it. No, tester. Oh, right, I was messing with the make file. I don't know. I'll see if I can get this thing to happen. Let's see. All right, I'm just gonna try something real quick. Wait, so question. Right, so when you call make check, are you saying here, Cody, that the print statements aren't happening when you do make check? Because if you look at my main, you'll see that I'm printing stuff. Well, I mean, if your text is even slightly off by one character, it'll throw you off. Ah, well, I think that's your trouble. Yeah, you're trying to use print for debugging. The trouble is, like, if I do system.out.println, like, hi, it's me, Cody, and then I do make. Oops. You'll notice it says hi, it's me, Cody. But when I do make check, none of that appears here because it's intercepting all of our output. If you want to actually see the output, you have to go through and use the the debugging section later. Oh, the remote debugger. Aha. So they're not even showing up. Interesting. Yeah, I'd have to look. We have to do some screen sharing. I don't have mine set up right now to easily remote debug, not this computer. Okay. All right, what's next? All right, I'm ready, Dana.
I mean, I guess I have another question for the ADTs and the BSD study guide. The B level problem 6, which is actually just like the 2014 midterm problem 1. I'm just kind of confused by that question.
Right. Okay. Okay. Do you agree with the first statement that in a, well, so first of all, the problem complete binary search tree, it's implicit in the statement of the problem, but do you know what they mean by it?
Not really, actually.
So it's basically saying if it's a tree where like it's just as big and bushy as possible. So it's like the prototypical, you have a root, everything has two children. Oh, there we go. The description is there actually. So in a complete binary tree, all nodes have either 0 or 2 non-null children. Make sense?
Mm-hmm.
Okay. So do you agree that in such a tree, a search always takes, I wonder why Paul picked theta there. We can always perform searches in worst case theta log n time. Do you agree with that?
Mm-hmm.
Okay.
Yeah.
So if we have a tree where every node has either 0 or 1 children, searches take n time. Do you know why that is?
Because then you could have like a stringy tree or something like
Not
that.
only could you, but you do, because every node has 0 or 1 children. So it's a long stringy tree, right? Does it make sense?
Mm-hmm.
Okay. So now suppose we have a search tree in which every node has either 0 or 2 children. Okay. What's the worst case search time? Ah, right. So this is a tree that's no longer complete. So let me do another notepad or paintbrush window here. Okay. I've seen some familiar characters there a second ago. Okay. So here we go. All right. So complete tree looks like. Those are going to be log n. Oops. Okay, so the question is, if it's not complete, but the only thing we require is everything has either 0 or 2 children, what might it look like? I'm trying to understand what this question is. A general binary search tree, which every node has 0 or 2 children. Okay, everything has either 0 or 2.
Wait, if everything has 0 or 2, isn't it just a normal binary search tree?
Well, I'm trying to understand what the difference is between this and the diagram I have up top. I guess the difference is, what? In contrast, in a binary search tree where every node has 0 or 1 children, I'm still having a little trouble understanding what the problem is asking. Like, for example, general binary.
Oh, if you want to go to Cody's question first, because I think he has it set up. So
Okay, one sec. I mean, I'm very curious. Does anybody have any idea? Like, this tree is not one where everything has 0 or 2 children.
Well, didn't like in the first sentence it say that a complete bushy binary search tree has 0 or 2 non-null children for every node?
Yeah.
Isn't that like what the last sentence is saying too?
Yeah, that's what I'm confused about. It sounds like they're saying in a binary tree, the runtime's log n.
They just told you the answer.
I'm gonna have to go to, I don't know what this problem means. Interesting. In theory, I mean, I'm pretty sure Paul wrote this question, but what on earth? Hold on. We're gonna figure it out. I'm so curious. We'll go to you, Cody, I promise, in just a moment. But I must understand what the heck's going on here. I'm guessing there's no solution though, since it's a fall semester. Yeah, oh, that's a mystery. All right, cool. We'll leave it for next time so I can shoot up with Cody because I don't want to just spin my wheels. If anybody has any thoughts, let me know. All right, Cody, let me give you the power to share your screen. We'll try and figure it out. You now have the power to share your screen. Okay. I can see your Zoom window. Oh, here we go. Yeah. Go for it. And since this is lab, I don't care that it's showing. Okay. All right. Well, if it's not working at all, we need to get the remote debugger working. It's super important for GitLab, by the way, Patrick. Okay. 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 Wait, go back. Can you show me that again? Where was there supposed to be a print? Because there was the right persistent, right story. Okay, I'll tell you when. So I forget, is the, okay. Right, I see, so this directory made is the part you're talking about. Oh, interesting. Okay, well, I have a video, I now have a screen capture of that. So I'll ask my TAs who built the remote debugging script, and I'll get back to you. Interesting. All right. All right, I will take back the screen. Thank you so much. Okay, let's see. All right, let's go back to that darn fall 14 question.
Wait, I think I found the solutions because like,
oh, really?
On the study guide, they linked it.
Oh, nice.
Study guide solutions, so.
There's a study guide solution for this one?
I think one of the TAs made it. I think Sherry or something.
Okay, cool. Okay, where is it? On Ed?
Do you want me to just drop it in the chat?
Yeah, please do. That way I don't accidentally expose anything on the screen that I should. Okay, now let's learn what the heck this question is supposed to mean. Oh, I'm so dumb. I get it. Okay. Right. Okay. Yeah. All right. I think I just panicked. Let's go back to my notepad window then. All right. I keep saying notepad. I meant paintbrush. Okay. There we go. That's what I was missing. Okay. This is a tree where every node has 0 or 2 children and it is not complete. Okay. So then yes, I know we just looked at the solution, or you did a second ago, but so what we want to know is, what does the worst case tree look like, right? So doing something over here isn't going to make it any worse. Does it make sense? Because like, it's just adding a node, but they're easy to search.
Mm-hmm.
Yeah, exactly. So the most lopsided tree we can get is just this right here. So that's the pattern we're supposed to observe. Sorry, I just gave up too quickly. Cool. This is an incomplete tree. All right. So what's the runtime on such a tree going to look like? What do you think? I'll take an intuitive answer, a formal answer.
I mean, I'm still kind of not sure because I don't know, intuitively it should be like what the solution says, like ON, but like, isn't there more nodes? Like,
sure. Well, here's a question. If let's say there's 1, 2, let's count them, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So in this total tree, there's 26 nodes, right? What's the height of this tree?
It's just 20, 25.
Nope, not quite. So that's 1, 2, 3, 6, 7.
Oh wait, oh shoot, sorry.
Okay.
No, that makes sense. Okay.
So 13 is the height, right? Okay. And so the runtime for the worst case search is going to be, if you happen to go to this bottom node, what's the more general relationship between n and the height?
Oh, so it's just n divided by 2.
Right. And so then that means the runtime is going to be that.
Okay.
Here's another way of thinking about it, though. This is just a spindly tree, right? Like here, with this extra, set of stuff glued on, but it doesn't really matter. Like it is just a spindly tree. It's the slightly different shape.
Okay, that makes a lot of sense. Okay, thank you.
Yeah, you got it. Cool. Good question. I enjoyed it. Alrighty, that's it for today. Okay, I will look into the mystery Cody and then hopefully get you an answer shortly. All right, see you guys Monday. And Monday, after we have that survey result, then finally, at long last, we'll do some kind of live survey thing. All right, see you then.